Hi, my name is Suraj. I'll be discussing the use of ordinary differential equations, ODEs, in material science. So, differential equations are equations from the derivative of one or more functions. We can use it, for example, to calculate the motion of an object. So we have the equation for displacement. So the velocity becomes the first derivative of this equation, which is 3t squared plus 6. Second derivative will give you the acceleration, which is 6t. Moving on. ODEs are an equation dependent on only one single variable. So you can see here dy over dx plus x equals to 6. We can rewrite that as change of y with respect to x equals to 6 minus x. Now, ODEs are used to formulate equations describing a change in a system with respect to an independent variable, such as x in this case. Moving on, we have quite a few different ODEs. So we have the homogeneous ODEs, which can be solved by separation method, Bernoulli's equation, exact ODEs, homogeneous second order ODEs, and linear ODEs. So most of these equations have their own way of being solved, either through a general solution formula, or we can use an integrating factor also. Now, in material science, I want to introduce to you Fourier's law of thermal conduction. So, Fourier's law states that the rate of heat transfer is proportional to the negative gradient in the temperature. Now, if we introduce ODEs to this law, you can see here that Q, being the heat flux, is equal to negative K, thermal conductivity, partial temperature over partial X. And we have a conservation equation here, which is partial rho over partial T equals to negative partial Q over partial X. Now, specific heat capacity is defined as the amount of energy required to raise the temperature of an object by 1 degree Celsius. So that's why we can call it the change in temperature of energy in an object with respect to the change of temperature. Now, to find the energy per unit volume of an object, we can use rho E of temperature. Now, if you want to find the rate of that, we differentiate it with respect to time. So after differentiating it, we get rho dE over d time, and that is indicative of the specific heat capacity constant, right? So we can substitute that. So now it becomes rho C partial T over partial time. If we substitute Fourier's law and this internal energy equation, you can see here now we get rho C partial temperature over partial time equals to, if we differentiate this with respect to x only, we get negative K second derivative of temperature with respect to x squared. Now, we move rho C to the other side, we get a temperature formula. So this denotes the change of temperature with respect to time, which we now call alpha, where alpha is now known as the diffusivity. Now, the use of this is to predict trends in change of material temperature with time. We can use it to determine suitable materials to use in extreme weather temperatures, like in a combustion chamber, in a freezer, and in a boiler, because changes in temperature can cause a change in stiffness and also strength. Thank you.